So like I said, I'm Tom Berlin, and I'm presenting the solver for very large systems of partial differential equations. I'm in the chemical and biological engineering department, and I am a senior. So I'm going to talk first about some real-life examples of problems that would use this kind of solver, and then give the mathematical background behind one particular example, and then the algorithmic background behind the solver algorithm that we're implementing, and then some things that we would like to add to that. So one example when you have this very large system of partial differential equations is when you're simulating flow of oil and gas through underground reservoirs. So like say you have this oil field and you want to know where you should drill a well so that over a 30-year time period you get the most production from the well, from the field. In this case, you're interested in the distribution of pressures over the whole field. Another example is if you're simulating heat transfer over some object. So say you have this object you submerge in a water bath and you want some equilibrium temperature distribution across it. And so in that case, the variable of interest is temperature across the whole domain. Another example here is simulating flow of some, or diffusion with some analyte across a brain, which is an inverse problem for medical imaging. In this example, you're interested in the variable of some concentration across the whole field. So in each of these examples, you have some kind of a constitutive equation that relates some quantity to itself across the domain. So here the quantity is pressure, here was temperature, and here was concentration. So a particular example here is this temperature heat transfer problem. So in this case, you have the particular example we're using here says you have some square object that you drop into a cold water bath. So assume the water bath temperature say 0 degrees. And over a period of time, you expect to get this kind of temperature distribution, where on the edges it's cold, which is the temperature of the surrounding fluid, and in the center it's still warm. So because computers can only deal with a continuous temperature distribution, can only deal with discrete temperature distribution, not continuous, we have to conceptually divide the whole domain into a series of points. So here we have, I think, 16 plus, 25 total points. So we further divide this into the interior points, which we labeled omega here, and these boundary points, which we call gamma. And the significance of that is that because it's surrounded by this well-mixed fluid, we know the temperature on the boundary. It's called the Dirichlet boundary condition. So we said it was equal to 0, the temperature of the fluid, like say it was an ice water bath, then the temperature would be 0 degrees C. So really what we want to find is this vector of temperatures across the interior of the object. And so we call that vector U here, and our little example has 16 points. So again, the equation here is this just the heat equation, or Fick's second law of diffusion. And by virtue of the fact that heat doesn't accumulate or leave from any particular point in the domain, that is to say there are no temperature sinks or sources, we can set this right-hand side equal to 0. And then we get this simpler equation, which is called just the Laplace equation. But it has this sort of mysterious operator here, this nabla squared. So what that actually means is the sum of the second unmixed partial derivatives of the variable of interest, which in this case is that U, the temperature. So just because this is a two-dimensional problem, this is what it expands to. But if you had like a third dimension, you'd have a third term that would have Z in the denominator, and you could do it also with polar coordinates or radial coordinates or anything. But again, this is a continuous version of the problem, and a computer has to have some kind of a discrete version. So somehow take this nabla squared and change it into just a square matrix A, which gets multiplied by the temperature vector U to have the same or a similar effect to taking the Laplacian of that U. So again, we said we're looking at the unmixed second partial derivatives of that quantity U. So if you're approximating a first derivative, you do this rise over run. So you have some change in some value, divided by the distance you travel to make that change. So if we're approximating the first derivative between
What
Q here.
the symbol means is U sub I plus 1 here, that means
So the rho is,
at the point, at that point, or?
it's just general. I could have probably put more dots around there to make it seem more generalized, but
Yeah, but
this
that means the partial derivative against X and the J.
No, these are particular values at those points. So the first derivative you approximate with this difference here divided by the distance between those 2 points there. And that'd be that forward difference. And you approximate this derivative with this minus this divided by the difference. So that'd be a backwards difference. And so then you approximate a second derivative by looking at a difference in first derivatives, the forward and the reverse, and then dividing by a distance, so it's a central difference.
Okay.
That's why this approximates the second partial derivative there. There's the forward and the reverse, and then the distance in between. And we can do the same thing with respect to y. We have this derivative, and the difference between them divided by the distance. So again, the Laplacian is the sum of those. So you add them up, and you do the algebra, and it works out to this 1, 1, negative 4, 1, 1 coefficient pattern. Which is helpful because then we do every single point in the domain, we get that same, you see this pattern here again, 1, 1, negative 4, 1, 1. So now this whole matrix approximates that Laplacian operator on the temperatures across the domain U. So still, this is what we really want to find, these temperatures, but they're bound up in this left-hand side with the A beside them, this whole big matrix. So classical ways of getting the vector temperatures out of the matrix equation are Gaussian elimination is the direct method. The advantage of that is that it's accurate, but it's another advantage is that you know exactly how long it's going to take, but a disadvantage is that it will be a very long time that it will take. Iterative methods are an alternative to this. Good thing about them is that you can make a trade-off as you choose between accuracy and speed, but they might not actually be converged to the right answer, and the accuracy might be pretty low for a reasonable amount of speed. So the multigrid method, which we're implementing, it involves a combination of these two methods to get both accuracy and speed. So again, what we know is these boundary points, and what we're trying to find is these interior points. So right from the beginning, we do an iterative method to approximate these interior points. And so because it's only approximation, there'll be some kind of error or a correction that we want to add onto that to get the actual value of the points in the interior. So to get that correction, we conceptually take this interior and only look at every other point. So as we define a coarse set of points. And on this coarse set, these 4 points in this example, we actually do a direct solver to solve for the correction. So this correction is what we want to add on to the approximation to get the actual value inside here. But we've just solved at these 4 points, and we want it across the whole interior. So we have to interpolate, until we have correction across the whole of the interior here. And then when we have a correction, this is right here, no, this is the correction actually. You can add it onto our approximation to get the actual value on the interior. And at that point, we know the interior points, we already knew the boundary points, so we know the temperature across the whole of the object. So the reason that we did the coarsening was because at that coarse level, there was only 1/4 as many points as in the full level. And we did a direct solver at the coarse level, which means that if we had the full number of points, it would be very slow. But because we coarsen like that, it's acceptably fast. But this is only 2 levels of resolution we used here. So you can go further by doing a 3rd level resolution, at which point it would have 1/16 as many points, and that's just for a 2-dimensional problem. If it was 3-dimensional, you'd have 1/4 or 1/8 and then 1/64 as many points. And so, because at this level, you are just solving another matrix equation, another A equals B, you can use all the same logic you used at this level to define, to do an iterative solution, and then say this is the kind of correction that I want to this iterative solution. And then you get the correction here, which corrects this one. And then the solution here is itself correction at this level. And so you can actually extend this as many levels as you want, which is why it's actually called multigrid, not just 2-grid or 3-grid. So yeah, it calls itself recursively, that is. So one thing that we want to add on to this, and in fact the reason why we're re-implementing this in the first place is to actually parallelize some of the steps of it. So in the example of the interpolation step, when you interpolated this central point from these four, which we just took it as an average, that operation is completely independent of taking this average here, or this average here, or however you choose the interpolation. You can make all three of those happen at the same time rather than one after another after another. And so just in this limited case here of these few points, you get theoretically a 3 times theta. A few methods for ways to parallelize things would be across the central processing unit. So many, like 2 or 8 or 4 cores of computer, or the graphics processing units, which might have something like 512 compute units. Or these other options are between computers, MPIs, computers in the same room. Grid computing is more like computers geographically widely spread apart. So I want to thank Dr. CJ for helping me with all the math behind this. He will help me conceptually understand reservoir simulation concepts, and Dr. Carlson, who pointed out in the first place that there is no nicely parallelized Python implementation of multigrid. That's the way I had it. So, anyone has some questions?
So what is the conclusion of you try to develop a method for estimate the solution of the differential equation?
Yeah, so go back. The equation. So in this particular example, I've defined temperature as some kind of, in terms of partial differential equations, but you have to, it's you have to implicitly solve for that temperature, and then you could use that in some kind of a time-stepping simulation to get temperature at each step, and you could visualize how the temperature goes from hot all over the object, and then it smooths out, and eventually it would cool down to flat. So that would just be this temperature example.
So you end up with solve this Laplace equation.
Yeah, well that's just the example we've used, so and that implied this particular coefficient matrix. But if you did some other differential equation, you get a different coefficient matrix here. But after that point, the multigrid method or any systems of equation solver doesn't care what the original differential equation looks like. It just has some kind of a coefficient matrix, an unknown matrix on the right-hand side. So actually, the original problem we're working on was this reservoir simulator, in which case this matrix is pretty irregular, actually. It's not so nice and smooth integer coefficients like this. That's a big reason why you can't actually just use some algebraic, like this heat example, you could solve it by hand with just some algebraic method. And you could use some kind of symmetry argument to actually solve what you think the pressure or the temperature distribution will be. But if it's a very inhomogeneous medium that something is diffusing across, then you can't do that by hand because it's actually dependent on some data, which would be, say, for example, the transmissibility of some fluid going through a rock.
So instead of solving that Laplace equation, you end up solving this matrix equation.
Right. That would be
using this approximation or estimate method.
So you got it.
Yes, that's right. That's right. After converting that continuous problem into a discrete problem, we end up with this equation.
Yes. So the key example is a little bit misleading because it's something you could do algebraically, but something has a bunch of different, where the equation is slightly different at every point would be something you couldn't necessarily do by hand. The example of pressure. Okay, so this one. Oh, this is a good example here. So here the Laplacian is actually broken up by this diffusion tensor in between. And this actually takes a different value at every point across the domain. So this tells you basically the transmissibility to diffusion. And what that really means is the fact that you have these neural tracks pointing in different directions. If the neural tracks point this way, diffusion will favorably occur in this direction and will not likely to occur in this direction. But that's totally different over here, or it might go in a different direction. So the inverse problem of this is where they actually look at the movement of the fluid and they estimate that diffusion tensor across the whole brain, and that gives information about which direction neural tracks point. So it's easier to set up for this, for the solver's example. The other example, the other direction where you have the diffusivity, you want to find the concentrations. But the point is that this is totally different across the whole domain, so you couldn't solve it algebraically. You have to do it numerically. But that relies on some discretization of that particular differential equation.
Yeah, the heat equation, this particular one is fairly simple. It's set to 0. Is there a limit how complicated the differential equation can be for this method to still work?
I think it has to be some kind of a linear operator on the interior, on the interior points.
What if du dt wasn't 0? And would this method?
It just well, you have to have some kind of a condition for the right-hand side, but if you have that depends on other elements of your simulation. Like you could set it up so that you recalculate the right-hand side at each little step. But if you can calculate so it's some kind of a static value, then it might be not necessary to define this particular value, like this is defined as 0, but then you would have a constant on that side. So I think in our pressure equation example, the whole scheme is you solve for some pressure differences, and you use those to estimate flow in and out of cells, and then the new flow sets up some saturation of oil or water in a cell, which itself tells you what is this coefficient. This coefficient here is dependent on the concentration. So that would make this here itself not actually constant, but you would solve that with some other equations which are actually a lot faster to solve. The slow step in any one of these is solving the equation where for the unknown value that's within the differential operator. So it answers the question is it depends on how you set the rest of the simulation. But basically, if you have some kind of a square matrix and a column vector that's unknown and a column vector that is known, then you can solve it with this sort of method.
And so it's a question of time. How long it takes to do?
Yeah, but this still is a slow step. The other parts are much quicker. The setup parts.
Yes, indeed. The fun stuff that the result of this is fed into something else that can change with time. So within a certain time, you assume that things are linear. So the linearize the process in time, and then use that to change things. That's what I would have.
So this temperature distribution is one particular equilibrium distribution at one time step, but you have to solve this matrix equation several times for each independent time step that you want, whatever temporal resolution you have in your simulation. You wouldn't do this just once per simulation, you do it many times.